In the previous lecture, while discussing the energy conservation in central force field, we have obtained the expression for the total energy of a particle moving in a central force field. And you have seen that the total energy E of a particle of mass m moving in a central force field is given by this formula, that is E equal to V plus J square over 2mr square plus half mr dot square. Although in the previous lecture, instead of this V, I have used the symbol U. Actually, you know that this V or U is actually called the central force potential or central force potential energy. In fact, in higher physics, the term potential is used instead of potential energy. But whenever we say central force potential, that means potential energy. Okay? So in quantum mechanics and also in classical mechanics, in higher physics, we always use the term potential instead of potential energy. You may call it potential energy, that is okay, but you may also call it simply potential. Okay? So don't confuse between these two terms. Here potential means potential energy. Actually, this potential V is the potential energy of the particle due to the interaction of the particle with the central force field. It means the central force acting on the particle is responsible for this potential energy V. And the second term in this expression, which is J square over 2mr square, this is actually called conventionally centrifugal force potential or centrifugal force potential energy. Actually, the main purpose of this lecture is to clarify why we call this term centrifugal force potential or centrifugal force potential energy. The main purpose of this lecture is to clarify this fact. Lastly, you will see that actually this is not any potential energy, but why we call it potential energy, we will see in this lecture. Okay? So this lecture is very interesting because here this term centrifugal force potential is actually in this name is actually misnomer. It misguides. We think that there will be a potential energy of the particle corresponding to the centrifugal force, but this is just a misconception. But why we call it, why we name this potential like this, we have to understand. Okay? So we will actually discuss both of the potential in this expression. First one, which is called central force potential or potential energy. First of all, we will see how it is defined and how it is measured. Okay? As I have told you that this V is nothing, this is simply the potential energy of our particle moving in the central force field due to the central force acting on it. Because you know that whenever a particle is interacted by some conservative force, then we define potential energy of the particle relative to that conservative force. So this V is the actual potential energy of the particle due to its interaction with the central force field. Okay? And so it can be measured by the usual method. You have studied in the lower classes how potential energy is defined or how potential energy is measured. Actually, potential energy, you know, is a state function. And so, whenever we want to measure the potential energy, it is impossible to measure it. Always potential energy, always change in potential energy is measured, never potential energy. But if you want to measure potential energy, definitely you have to consider a reference point or a reference state of our system in which we arbitrarily assume that the potential energy of the particle or system is zero. In the reference state, we assume it. never say that potential energy is actually zero at that point. It is just a convention, or it is just we take a reference and assume that the potential energy at that point, whenever the particle will be there, will be zero. Okay, and so potential energy of a particle at a given position will be different if you take the different reference. In case of different reference, the potential energy of same particle at same point will be zero. For example, if you talk about the gravitational potential energy, and you think that a particle of mass m is lying at the surface of the earth, okay, and you consider that the surface of the earth is the reference level, then you simply say that gravitational potential energy of this particle is equal to 0. And if it is at a height h from the reference level, you simply say that the potential energy at this position is mgh. But if you consider that the reference is not at the surface of the ground, then potential energy of this particle at this position will be not mgh. Okay, if we consider the reference h height above, then at this position potential energy of that particle will be simply zero, because the particle is lying at the position of reference. So, and reference selection is completely arbitrary, although we see the physical situation for selection of reference, but there is no any certain rule for selecting reference. Reference selection is completely arbitrary. Okay. So in a work energy chapter in lower classes, definitely you have studied this potential energy and how it is measured. Actually, potential energy is measured by calculating the work done by the force which is actually acting on the particle. In fact, when you bring a particle, let us say from a reference position, see here this figure, this point, let us say O is a reference point, and a particle is brought from any arbitrary path to a test point P. Test point means the point where we have to find the potential or potential energy. Then the potential energy is simply measured or simply defined as the work done by the external agent in bringing this particle from the reference level to the test point in such a way that its acceleration is always zero. Have you understand or not? If you want to measure the potential energy of a particle at this test point P, then you have to bring that very particle from a reference level. Reference levels means or reference point where you simply assume that potential energy of the particle is zero. And brought this particle, an external agent brings this particle from this reference level to this point P. But how it is brought? It is brought in such a way that its acceleration always remains zero. It is never accelerated. In other words, you can say that the particle is brought in such a manner that it always remains in the state of quasi-static equilibrium. In that condition, the work done by the external agent in bringing the particle from reference point to the test point is simply equal to the potential energy of the particle at this point P, that is at the test point. So mathematically, we simply define that the potential energy V of R or potential V of R is equal to integral R reference to R, where R is actually the position vector of this test point P, F external dot dr. This is just the definition of work done. Okay. So I think you have understand. If you want to find the potential energy or potential of the particle at a particular point, then you have to bring that very particle from a reference point where we assume that potential of the particle is zero to that test point, in such a way that the acceleration of the particle always remains 0. Okay. Now, as you know that this particle, if we think about the particle moving in a central force field, then apart from this external force, the force exerted by the external agency which is bringing this particle from reference point to the test point, apart from this force, the internal force, that is the central force in which the particle is moving, is also acting on the particle. Here central force which will act on the particle will be called internal force, okay, or internal conservative force you can say. So as the acceleration of the particle is 0, so net force on it will be 0. And what will be the net force? Net force is F external plus F internal, and that will be equal to mass into acceleration, but acceleration is 0, so this is 0. As I have told you that in the present situation, when we consider that particle is moving in a central force field, then this internal force means the central force acting on the particle. So F external plus F of r, here F of r is what? This is central force acting on the particle. That will be 0. And so this external force is equal to minus F of r. So definitely in calculating the potential energy, always the external force is equal and opposite to the internal force. That is internal conservative force you can say. Okay. So in the defining equation of potential energy, that is equation 1, now we can replace this F external by minus F of r. So V of r may be calculated by this formula, minus integral r reference to r F of r dot dr. Okay. So see, in terms of external force, when you measure the potential energy, then here there is plus sign, and if you are calculating this value of potential energy in terms of the internal conservative force, then there will be a minus sign in this formula. So this is the general formula or general technique to calculate the potential energy. We are actually talking about the potential energy in of a particle moving in a central force field. So here this F of r refers the central force acting on our particle. Okay. Actually, I will illustrate this idea by taking a proper example. So let us take an example to clarify it, so that the concept will be clear to you. Let us consider that there is a particle of mass m which is at a distance r from the center of force. Center of force means this particle is acted upon by a central force, and that at any moment the distance of this particle is r from this center of force, and we want to calculate the potential energy of this particle when it will be at this position P. Let us say P. What will be its potential energy? Okay. What is the technique? You have to think a reference point. So let us, for example, we define the central force acting on this particle. So let a particle is moving in a central force field. Central force field. And at any moment it is at r equal to r from the center of force. From the center of force. And you have to calculate what will be its potential energy due to its interaction with the central force in which it is moving at this position. It means you are going to find what will be this V of R. In fact, for finding the value of V of R, definitely we have to know the central force which is acting on this particle. So, for example, let us consider our particle is moving in a force field which obeys inverse square law. For example, gravitational force, electrostatic force. And in such a field, this particle is moving. Let us consider. So, let this F of R, it means the force acting on the particle, let us consider, is given by K over R square R hat. Let us consider. You can see this force is actually an inverse square law force because this force is inversely proportional to R square. And here K equal to a constant. And this constant may be positive or it may be negative. You know, if K is positive, then you have studied earlier that this force F will be in fact a repulsive force. Okay? This will be a repulsive. And if K is negative, for example, gravitational, in case of gravitational force, this K will be equal to, in fact, minus Gm1 m2. Okay? Minus Gm1. Then what will be F? F will be, in fact, attractive. So this constant K may be positive or it may be negative, and accordingly the force may be repulsive and it may be attractive. Okay, so taking this example of force F of R, now let us try to find what will be the potential energy of this particle when it is situated at a point whose position vector is R. Okay. Now, as I have told you, for calculating the potential energy or potential, first of all, we have to think about the reference point. So, what will be the suitable reference in this case? This is not a rule. I am again telling that reference selection is completely arbitrary. We can consider any point as reference point. But what will be the suitable reference that we should think? As I have told you, in case of central force field, generally people think about a reference where force becomes zero. Are you getting the things? If F is zero at a particular point, then that reference selection will be more convenient. It is not a rule. That will be convenient. So you can see here, if we take R equal to infinity, then what will be F? See the expression. F of R in that condition will be F of infinity, and that will be 0 because here R square is in denominator. So in the present problem, reference selection at R equal to infinity will be more convenient. Again, I am telling that this is not a rule, but for convenience we select such a reference. So in this case, we consider that R reference is equal to infinity. Okay? And therefore, when you will find the potential at the point P, where actually the particle is situated at a distance r from the center of force, then what will be the potential energy? We will use actually this formula C here. Okay. Now, as I have told you that this K may be positive or negative. First of all, we consider that K is positive. K is positive. First of all, we consider. So, V of R will be what? This V of R will be equal to minus integral. Now reference for reference r is infinity, so we will take here infinity and r, and f of r a dot dr. This is just formula. Okay. Now see, f of r, this is k over r square r hat. Okay. So this is minus integral infinity to r, and f of r, this is k over r square r hat, and dot, and this dr can be written as dr r hat, because dr vector is also in the direction of r hat. So what is our result? You can see k is constant, so take it outside of the integral. So minus k integral infinity to r, and r hat dot r hat, you know this is equal to 1. So this will be simply dr over r square. Okay, dr over r square. And this is minus k. Now you know integral of 1 over r square will be what? Integral of 1 over r square is minus 1 over r. And limits are r and infinity. Okay. So now this will be 1 over r, a minus, sorry, k over r, a minus k over infinity. Okay. And this will be simply k over r. So if you consider that constant k is positive, that is force was repulsive, then V of r in this example will be equal to k over r. Okay. And if you think that this k is negative, if k will be negative, then what will be our result? You can see this Vr will be simply then minus k over r. So we also say flatly that in case of the repulsive central force, potential function is positive, and in case of attractive central force, the potential function is negative. For example, in case of gravitational interaction, as you know, gravitational interaction is attractive, so gravitational potential energy is always negative. Okay. But electrostatic interaction may be repulsive, it may be attractive. So in that condition, potential function may be positive or may be negative. Okay. So I think you have understand the potential concept for the for regarding the central force. Okay. Now, as I have told you earlier, that our present the main aim of this lecture is to clarify this term. J square over 2mr square is known as centrifugal force potential or centrifugal force potential energy. Why it is called potential energy? Although it is not potential energy, you will see in this discussion, but due to some reason, for convenience, we call it potential energy due to centrifugal force. Okay. So now we will talk about the centrifugal force potential. Centrifugal force potential. See here, the page has been turned, but this is now okay. See here. Centrifugal force potential, or potential energy you may call it. And this is actually given by the expression what? This is J square by 2mr square. This term in the expression of energy is known as centrifugal force potential or centrifugal force potential energy. Why it is called centrifugal force potential or centrifugal force potential energy, we will see here. Definitely you have studied in your lower classes the concept of centrifugal force. During motion in a rotating frame, we studied the centrifugal force. You know, actually the centrifugal force is a pseudo force. It is a fictitious force. It is not a real interaction. Centrifugal force is not a real interaction. It is not a real force. Whenever our aim is to write equation of motion in a rotating frame which is non-inertial, then we have to consider this pseudo force for writing the equation of motion. And so this is just a mathematical technique. It is not a real force, real interaction. Okay? But it is treated like a force in when we discuss the motion in a rotating frame. Then we consider it. But don't think that this force is a real force, actually acts on a particle. It never acts on a particle. Okay? But why we call this potential, this term as centrifugal potential, we will now see it here. Now, can you remember the expression for the centrifugal force, which is actually a pseudo force? And centrifugal force, definitely you have studied it. So centrifugal force. If we denote this centrifugal force by the symbol Fc, you have studied that this is equal to mv square over r, or equivalently you also write it m omega square times r, and equivalently you write it m r theta dot square. Actually here this theta dot is equal to d theta by dt, and this is equal to omega. So Fc is simply defined as mr theta dot square. Now let us suppose that this is an actual force. It is not an actual force. It is not a real force. But I am saying you, if we treat that actually this force is acting on our particle. Actually this force is acting on our particle. And we can associate a potential energy with it. Then what will be that potential energy? Our aim is to find. But before that, we will change the expression for this centrifugal force in terms of the angular momentum of the particle. Now you know the angular momentum, which is denoted by the symbol J, you know this is equal to what? This is mr square theta dot. Okay? mr square theta dot. So what will be actually the value of theta dot? You can see this will be J over mr square. So now let us substitute this value of theta dot here. So in terms of angular momentum J, this centrifugal force can be written as Fc equal to mr times theta dot square. Theta dot square will be what? This is J square, see here, J square over m square r4. And this will be equal to J square over. This mr will cancel, and in denominator there will be mr cube. mr cube. Now, you also know that when a particle actually moves in circular orbit, the centrifugal force is in radially outward direction. So this Fc can be written as Fcr hat. Okay? So in vector form, you can write this force Fc as j square over mr cube r hat. Okay, so this is the expression of the centrifugal force in terms of the angular momentum j of our particle. Now, as I have told you, this is not a real force. This is not actual force. In fact, we cannot associate any potential energy with it. This is the fact, because potential energy is due to the real interaction, between different constituent, different parts of a system, and that interaction must be conservative. But this force is not a real force. Actually, it does not act on our particle. But for a time being, let us consider that this force is a real force. Consider it. It is not real, but I am saying you that consider that this force is actually acting on our particle, and we can associate a potential energy with it. Then what will be the potential energy? This is our problem. Are you getting the things or not? This is not a real force, but I am saying you that you consider that this force actually acts on our particle. Okay, and it means we are treating this force for a time being just as a conservative force acting on our particle. Then what will be the potential energy with respect to this interaction or this force? Again, you can see here, when r is equal to infinity, see this expression here. You can see that this Fc will be equal to 0. So in this condition, if we want to define potential energy with respect to this force Fc, then the most convenient reference point will be again r equal to infinity, because when r is infinity, Fc is 0. So I have told you earlier that for the convenience of selection of reference, we simply take the reference point where the force vanishes. This is just for a convenience, for simplicity, not this is a rule. Again, I am telling you, because reference selection is purely arbitrary. It is not a rule that where force will be 0, only then you can consider the potential energy there 0. Potential energy can be taken 0 anywhere. Okay? But for convenience, again, I am taking r reference equal to infinity. Okay, and our aim is again to find the potential energy due to this centrifugal force at a point where r is equal to r. So what will be this potential energy? So potential due to Fc, potential due to Fc. Okay, if you denote this potential by, let us say, Vc, then what will be this? This will be minus integral infinity to r Fc dot dr. This is the general formula for finding the value of potential or potential energy. Now let us substitute the value of Fc here. You can see this will be what? Minus integral infinity to r, and Fc, you have just seen that Fc is equal to what? This is j square. See the expression. I have obtained it here. J square by mr cube. J square over mr cube r hat and dot dr r hat. Again, this r hat dot r hat will be 1, and you know that in a central force field this j remains constant. So this will be simply minus j square over m and integral of dr over r cube. Okay, and limits are infinity and r. Okay, when you will evaluate this integral, you can see this result will be simply what? This is simple integral. I am just writing the value. This will be equal to j square over 2mr square. See this result. And as in the expression of energy, this term comes j square by 2mr square. You can see this is our term, j square by 2mr square. So, as this term has been obtained, simply treating the centrifugal force as a conservative force, as an actual interaction, and then we see that if we imagine that the centrifugal force is actually a real force, a real conservative interaction, actually it acts on the particle, then the potential energy due to it will be this much. And that's why we call this term centrifugal force potential. This is the reason. This is the reason. But as I have told you, that actually this name is misnomer, because as we have studied earlier, that potential energy signifies configuration which emerges out of interaction among the constituent particles of the system. Okay? But centrifugal force is a pseudo force. It is not a real force. It is fictitious. And hence, there is no physical interaction responsible for it. Okay? So, we cannot have a potential energy corresponding to this force. Okay? Never we can associate potential energy with a pseudo force, because pseudo force is not a force in real sense. But taking this force as a real force, the expression comes out same. That's why we, for the sake of convenience, we call this term what? This term is called centrifugal force potential. I think you have understand. Actually, I am writing these things in brief here. Actually, centrifugal force is not a real force. A real force. It is a pseudo force. Pseudo force. We can not define potential with respect to it. So never think that actually this is potential energy due to the centrifugal force. Never think it. Sorry, I am suffering from cold. So sometimes I am coughing. Okay. Then I think you have understand this fact. Now, actually, this term which we have, which is called centrifugal potential, centrifugal force potential. Actually, that is a kinetic energy, and that fact have been discussed in the earlier lecture by me. You have seen. In fact, you can see here that Vc, which is called centrifugal force potential, and its expression is J square by 2mr square. Okay. Now see, J square, this is, you know, J is equal to mr square theta dot. Okay. So this will be mr square theta dot square and over 2mr square. And what is this? This will be 1 over 2 m r square theta dot square. But you know that this v theta, that is transverse component of velocity of the particle, is equal to r theta dot. So actually this Vc can be written as half m v theta square. So actually this term is a kinetic energy term. This is actually transverse kinetic energy. This is equal to this is transverse kinetic energy. It is transverse kinetic energy. You can see here. This is transverse kinetic energy, not a potential energy. Okay. But for convenience, as I have told you, that we say that this term is a potential term, this is a potential energy. This is for convenience, but this is in real sense, this is kinetic energy term. So for convenience, here we will introduce a new term which is called effective potential. Effective potential. In the discussion, we will use now the term effective potential or effective potential energy, you may say. And that effective potential is denoted by the symbol VE, and this VE will be equal to what? This will be central force potential. And when we say potential, that means potential energy. Central force potential V and plus centrifugal force potential. Centrifugal force potential. And that centrifugal force potential is equal to what? This is J square over 2mr square. Or symbolically, you may say that this effective potential VE is equal to this V of R plus J square over 2mr square. J square over 2mr square. And therefore, when we write the expression for total energy, you can see the expression for the total energy which I have mentioned in the first line in the present lecture. You can see here. This is the expression for the total energy, and total energy is equal to V plus J square over 2mr square. Now V plus J square by 2mr square has been termed as effective potential, and this is actually the radial kinetic energy, because r dot, you know, is known as radial velocity. So this is radial kinetic energy. Okay. So in terms of this effective potential, you may now say that the total energy of the particle can be written as effective potential plus radial kinetic energy. Plus radial kinetic energy. Okay? Plus radial kinetic energy. So I think you have understand what does this term centrifugal force potential means. I am again repeating the fact that actually this is not a potential, this is not a potential energy, because it has been defined with respect to the centrifugal force, which is actually a pseudo force, and we cannot associate potential energy with a pseudo force, because potential energy is always associated with real conservative interaction. Okay? Real conservative interaction. Now, in terms of this effective potential, we can actually express the condition for a particle moving under a central force field. So in a central force field, you can see that E is equal to what? Now we can write this is VE plus half mr dot square. Okay, and half mr dot square will be equal to what? This will be equal to E minus VE. Now you can see that this half mr dot square can never be negative. This cannot be negative because it is kinetic energy, and kinetic energy is never negative. So we simply say that this should be greater or equal to 0. And this is actually the condition for the motion in a central force field. So you can say that motion in central force field, motion in central force field is possible. Motion in central force field is possible only when E minus VE is greater or equal to 0. This is the condition which must be satisfied for motion of a particle in a central force field. Motion in a central force field will be possible only when E minus VE is either equal to 0 or greater than 0. This should be never negative. When it will be negative, motion is not possible in a central force field. Okay, so I think you have enjoyed this lecture, and again we will come with another video on the chapter central force field, and like the previous video, you will again watch this video as I hope.